will open a share tray. So we can able to find attached file in your Teams files folder named with unit 2 compressors. So you can refer that. Just I will share that here. Can you able to see the presentation? Students, can you able to see the presentation?
Yes, sir.
Okay, so today in this class, we are going to look at the compressors. So that is for compressed air system. So the scope for this is various types of compressors and their characteristics have to be studied in this class. Then measurement of power consumptions, free air delivery, operating pressure, isothermal power required, and volumetric efficiency also to be considered while choosing the compressor. Then measurement of inlet air temperatures also to be studied in this class. Then the effect of inlet air temperature on power consumption. Also the assessment of specific power consumptions by the scope to study the compressors. So the effect of the following energy consumptions were employed in the compressor. So one is dust in inlet air, then dryness of inlet air, then inter and after cooler temperatures and pressures, then delivery pressure setting, then size of pipe, filter choking, then pressure drop piping layout, then belts and fitting losses that will affect the fittings of different types of types and sizes. So these are all the features of the compressors. So we have to be careful on these features. So we will look at that what is that one by one later. So also variable speed drive for a compressor operation and its assessment. Be careful. Then compressor capacity assessment. Then capacity control methods. Then method of systems lead qualifications. Then detailed energy audit of a compressed air installation with the actual case study. So to be studied with these compressors. Then introduction about the compressors. So we will look the energy sources for operating equipments. Then why compressed air is used for the operating equipments. Then properties that make it important. Compressed air. Then compressors and their working principles. Then highlights of compressors and industrial systems. Industrial positions, right? So these topics we are going to look in this class. So the energy sources for operating industrial equipments. So on this topic, we have in today's world many methods are employed to operate industrial tools. Labels. So the industrial tools and equipments have many methods to employ to carry out the process work that these industries perform. But in manufacturing industries, power plants, or processing industries, there are always energy source that act on the equipments, actuating them and making them function. So we have lots of methods to activate the equipments. Then the commonly used sources are, direct electricity can be employed, and steam can be employed, then water can be employed, then industrial oils, also the compressed air can be employed to activate the sources. So in this we have compressed air as a source used in the industry. So also we can use direct electricity. Also, we can use steam, water, and industrial oils to activate the equipments. But compressed air is significantly used in any of the companies. So we have to look at what is compressed air. So for that, why compressed air? One of the major methods of actuation of industrial machines in pneumatic actuation, that action by compressed air. So it is nothing but air at a pressure higher than the atmospheric pressure is used as a medium to activate the equipments. Then it has been widely used as an energy source for operating simple to sophisticated equipments in mechanical, chemical, and other process industries. So in all the industries, we will use this source, that is compressed air source, for operating simple and sophisticated equipments also. Even though air is the most abundant natural resource on the planet, compressed air is one of the most expensive of a service to provide. You know very well, air is the most abundant natural resource. So if air gets compressed, we can use this source for some extents. The following properties of compressed air justifies why it's such an important energy source. So these are the properties why we are using air. So the elastic nature of the air, so you know very well, so which permits internal storage of energy. So elastic nature of the air will permits internal storage of energy, so that can be used for our applications. Then the non-toxicity. The main purpose of using air is non-toxicity. Then air gets low viscosity compared to other working fluids. Then no appreciable corrosive nature. So the all other sources have some corrosive nature, but in air we don't have that. So increased life of equipments can be obtained by this property. Then the compressors and their working principle is given here. So an air compressor is basically a device that converts power into kinetic energy. Right. So actually, this compressor is an electrical device that converts electrical power into a kinetic energy by compressing and pressurizing air. So this compressed air can be stored or can be released in a quick burst on command. So whatever we want, whenever we want, we can command to open the compressor. Then we can use that the compressed air wherever we want. Then compressors works on two parallel principles. So that one is ideal gas law, compressed air energy storage. Right, so that is PV is equal to MRT. You know very well about this formula. So here T stands atmospheric pressure, and V stands volume of the whatever the vessel. Then M stands mass of the air. Then we have R, the universal gas constant. Then we have T, temperature. Right, so all the parameters we are in capital letters, so we know what was that. Then therefore, to increase pressure, so you can compare the formula. So increase the pressure of gas, one has to either decrease the volume. So pressure and volume were in the inverse proportion. So if you want to increase the pressure, you have to reduce the volume or increase its temperature. So pressure and temperatures are in direct proportion. So if you want to increase the pressure, you have to reduce the temperature, increase the temperature, or both invariably. So we can get all the three parameters accordingly we want. Then compression of air creates heat. You know very well. So if you compress, the volume gets reduced. We can get exothermic. That is, heat can be generated, and the air is warmer after compression. You know very well. So if you compress the air, the temperature definitely will be increased in the air. So this CAE tells that principle. So that is PV is equal to MRT. So there are three ways in which these CAE systems can deal with the heat. Air storage can be, adiabatic, diabatic, and isothermal. So you know what is adiabatic, you know what is isothermal. The opposite of adiabatic is diabatic. Right. So the adiabatic storage continues to keep the heat produced by compression and returns it to the air when the air is expanded accelerate power. We know what is adiabatic storage. Then the opposite of this is diabatic storage. So this dissipates much of the heat of compression with the intercoolers into the atmosphere as space. So this is essentially wasting thereby the renewable energy used to perform the work of combustion. So these are the processes of CAEs. Then the also combustion, you know very well, and the expansion approaches attempt to maintain operating temperatures by a constant heat exchange to the environment. You know what is exothermal compression and expansion very well. So they are only practical for low power levels without the very effective heat exchanges. We have these three processes. Then in industry, the positive displacement air compressor works on the diabatic storage of energy. So the second process is used in the industrial positive displacement air compression. So actually, this positive displacement air compression is a type of compression. We will look at that in the next slides. And work by forcing air into the chamber whose volume is subsequently decreases. Right. So we will apply the force to get the reduced volume to compress the air. They are classified as reciprocating and rotary depending on how the air is guided into the chamber. So the next we have the classifications of compressors. So on that we have positive displacement air compressor. So we have two types of positive displacement air compressor. That one is your reciprocating positive displacement air compressor, and we have rotary positive displacement air compression. It's also the second equation is Bernoulli's equation. So that air will obey. So you know if you look at the fluid dynamics, the Bernoulli equation will state the change in pressure will be equal to change in kinetic energy. Right. So P1 minus P2 equal to half V2 square minus V1 square. So therefore we know V1 will be less than V2, means V1 will be greater than V2. Right. So you know very well. So P1 and then P and V are in inverse proportions. So vice versa. So this pressure of gas in motion increases at a constant its velocity. So here V1, V and you know this half mv square. In this equation we have V as a velocity. So if pressure gets increased, definitely the volume gets velocity gets decreased. Right? So this principle is employed in dynamic compressors, so which uses centrifugal force generated by spinning impellers to accelerate and decelerate of a captured air which pressurize it. So we have another type dynamic compressors. So we'll look at that what is later. So the compressors has these two working principles. Right. So one is our ideal gas law, and another is Bernoulli's equation. And the overview of industrial precision of compressors. So in industry, compressed air is so widely used that it is often regarded as the fourth utility. Right. So this is the air is the fourth utility used in the industry. So followed by electricity, natural gas, and water. Then about 8 to 10% of all electrical power used in industry to employed in the process of compression. Right. So in percentage, around 10% of electrical power can be used to activate this compression. So you can imagine that. So this compression is used to around 10% of whole electricity power in the company. Then this compressed air with the use of compressor is employed for all other purposes. And air compressors are used in a variety of industries for the following purpose. So you know, in industries we are using the air compressors. So for this purpose we are using these compressors. One is operating machinery like hammers, presses, etc. Then the compressors also for using supplying process requirements. The supply chain management can be controlled with these compressors. Then supplying air at a high pressure for chemical actions also require these air compressors in industries. And along with industrial pneumatic work, air compressors are also used to produce compressed air in the following process. So also other than the industrial applications, we have these applications also. So the vehicle propulsion can be made by the compressed air. Then energy storage can be done in the compressed air. Then scuba diving, you know very well. So this scuba diving is mainly the main applications of compression. Then air brakes are the application of compression. Then emission propulsions also propulsion, you know, jet propulsions. So that also a application of this compressed air. So we know very well. So industries, most of the industries, we are using our compressors. Also, all other these applications where employ the compressed air with the use of compressor. Then air compressors are machines with a very low overall efficiency. Right. So actually, these compressors only around 30% of the energy supplied to the compressor reaches the point of end use. So the approximately 10% gets to the point of use of electricity, right? So the remaining power is converted to unusable heat energy, and to a smaller extent is lost in friction, emission, and noise. So these factors need to be identified and analyzed for optimum performance. So this is the drawback of a compressor, right? Then the classifications of compressors. We have classification based on the positive displacement compressor. Then we have dynamic compressors. Then in the positive displacement compressor, we have reciprocating compression. Then rotary compression. In dynamic compressor, we have centrifugal compression and axial compression. So based on the motion, we can classify these compressors. Then selection criteria for compressors to be seen in the subsequent slides. Then compression of compressions also we are going to look at. So the thing is we have these four types of compressors. So we have positive displacement compressors, also dynamic compressors. So in positive displacement compressor, we have reciprocating compressor and rotary compressor. In dynamic compressor, we have a centrifugal compressor, also axial compressor. So with that one by one. So in view, these are the types of compressors. We know very well. Depending on the action performed on air, these types is depending on the action performed on air. Compressors are broadly classified as follows. We know very well positive displacement compressor and dynamic compressor. So this is based on the action performed on air. So you know what is displacement. You know what is dynamic. You know what is reciprocating. You know what is rotary. So reciprocating means up and down motions. So from and two motions. Then we have rotary motions means rotary is circular motion, and centrifugal, you know, like the centrifugal pump. Then we have axial. So based on the action performed on air, we can classify the compressors. So we can look what is positive displacement compressor. So in this compressor, pressure of the air is increased by reducing its volume in accordance with the ideal gas law. So you know very well this positive displacement compressor is purely the principle of the ideal gas law. So these are further divided into reciprocating and rotary compressors. And this is our reciprocating compression. So these reciprocating compressors are the most widely used type of compressors. So in these compressors, air compressed by the action of the piston. You know what is piston cylinder arrangement. So this is purely the application of piston cylinder arrangement with one-way valves and pumped into a air chamber. So this with the activation of this piston cylinder arrangement, we can get the compressed air. Then we can have the one-way valve in this one-way valve, we can connect the valve to the chamber. We can store wherever we want. So this is a reciprocating compressor. Then also we have subtypes of reciprocating compressors. So depending on the machine configurations and the geometry, so these compressors are available as a horizontal, vertical, then horizontal, opposed, balanced, and tandem compressors. So these are some subtypes of reciprocating compressors. These figures show you the horizontal opposed balanced compression. So so horizontal opposed balanced compression. This is your piston cylinder arrangement. Then this is also a piston cylinder arrangement. So horizontal. This was in horizontal. So from the name itself, we can identify that. This is horizontal opposed. So this piston cylinder and this piston cylinder are in opposite direction. So horizontal opposed balanced compression. So we can apply these two piston cylinder with the use of this single shaft. So apply this shaft. If you rotate this shaft, we can get the opposed compressors. So this will present in if this expand, this compressor gets expand, this compressor will compress. If this compressor is expanding, then this compressor will compress. This piston cylinder will compress. So we can get the horizontal opposed balanced compressor. So these are a type of reciprocating compressor. Actually, this principle is reciprocating. So from two motions, so we can get the reciprocating motion, and also we can compress the air. Then, depending on the capacity, these compressors can have a single or multiple cylinders, and can be single acting and double acting. So we can have the other subtypes also. So based on the capacity, we can classify that as single stage, very well, single stage and multiple cylinders. Also the single acting and the double acting cylinders. Piston cylinders, like piston cylinder arrangement. Then the compressors can be lubricated with the oil or non-lubricated. So we have two types also. So the compressors may be lubricated or non-lubricated. The lubrication will be purely on oil. Then the non-lubricated machines have higher specific power consumptions because as compared to lubricated oil. So because we are avoiding the wear. There is a motion, we need to provide a lubrication. So the main purpose of lubrication oil is to reduce the wear or frictional forces, to avoid frictional forces, right? So non-lubricated machines have higher specific consumptions, power consumptions compared to the lubricated types. So in lubricated type, we will avoid the frictional forces. Then, depending on the number of compression stages, there are single stage, or multi-stage compressors available. Then in multi-stage compressors, they are cooled in between the stage of compression with the help of an intercooler. So we will discuss this intercooler and multi-stage compressors in the Brayton cycle, regenerator Brayton cycle. So that is here. So already we discussed this. So if there is multi-stage compressor, this is in the arrangement. There is multi-stage, there is two-stage. Then in between we have intercooler. So we will reduce the pressure of this exit pressure due to the initial pressure of the starting stage. So we know what is intercooler. Why we place this intercooler in between the two stage. Right. So the actual PV diagram of this multi-stage compressors is here that we discussed earlier. So this is stage 1. Then this will give you intercooler. That actually we are reducing the temperatures, right? can see this. So you can see this blue line, sky blue line. So this is actually your isotherm, right? So you know what is isotherm? Constant temperature, right? So you can compare this state 1 and you can compare this state 2. The temperature will be in same isotherm. So that's why we are providing the intercooler. So the intercooler will reduce the temperature to the starting state, initial stage. Okay, so that is the purpose of intercooler. Then we have in first stage, we will compress the air. The pressure gets increased by the compression. Then we will reduce the temperature with the help of intercooler to the initial temperature T1. Then again we will do this second stage compression. So actually this is an isothermal compression process. Right. So the multi-stage compressors have the following features over single-stage compressors. The higher discharge temperatures of air, then the lower specific power consumption for a same pressure differential, right? The higher investment cost for applications with the high discharge pressures, so greater than 7 bar, and low capacities less than 25 CFM, cubic feet per meter. So then also we have reduced pressure differential across cylinders, then reducing load on the compressors components, thereby increasing life of the machine. So this is the advantages of go with the multi-stage compressors rather single-stage compressors. So you know the multi-stage compressors having advantages with the higher discharging temperature of air, then lower specific power consumption, higher investment cost, applications with higher discharge pressure. Then we reduce the pressure differential across cylinders. Right. So also it will reduce the load on the compressor components, thereby increasing the life of the machine. So for a parameter, choose the multi-stage compressors. Then depending on the method of cooling, they are also classified as air-cooled and water-cooled compressors. So you know what is air-cooled. So if air is used to cool compressor, we can call that as air-cooled medium. Then if water is used as a cooling medium, then we can call that as a water-cooled compressor. Then the single-cylinder compressors are generally air-cooled one, while multi-cylinder compressors are generally water-cooled. Right. So we don't need the single cylinder to get cooled by water. So that air is enough to cool the single cylinder. But in the case of multi-cylinder, we need a water-cooled system. Then water-cooled systems are more energy efficient than air-cooled types. Right. So efficiency-wise, we can compare the water-cooled system are more efficient than air-cooled types. So also we have the variant types of reciprocating compressors available. Diaphragm compressors. Really, this is a rubber application. You know what is diaphragm. So these diaphragm compressors are also available there. So it's a variant of type of reciprocating compressors. This also comes under the reciprocating compressor type, which uses a flexible membrane, usually made of rubber or silicone. Like so, this membrane. So this is your membrane. This is your membrane. So we can compress this membrane. Right. So we can compress this membrane. We can retract it back. So this volume can be changed to get the compressed air. Right. So this diaphragm compressor is replacement of a metal piston with the rubber or silicone diaphragm. And due to limited stiffness, the limited stiffness of these materials like rubber and silicone, these are used in pressure applications like compression of hydrogen or CNG alone in the industries. So we are using the diaphragm compressor, the applications of compression of hydrogen and CNG gases. Right. So Then we have another type, an ionic liquid piston pump. Is a highly efficient hydrogen compressor which employs a liquid piston instead of a metal piston. Right. So we have we no need to go with the metal pistons alone. So we have diaphragm pistons, and also we have this liquid pistons also. To compress the hydrogen up to 450 bar is available with the use of this liquid piston pump. You can imagine from this diagram. So this is actually your liquid piston. So we have a pump chamber, then we have a pump check valve, then here we have expansion chamber, then we have if inlet there we have exhaust, then we have a combustion chamber, then we have a combustion valve, then we have a magnetic latching. So we no need to go in detail with this type of compressors and principles. Just have a look at the types of compressors alone. Types also liquid piston pumps also available to get the compressed air. Right. So it works on the principle of poor solubility of hydrogen in ionic liquid. So the heat exchanges that are used in a normal piston compressors are removed. Then as heat is removed in the cylinder itself where it's generated. So this is actually we are using a liquid piston. So the heat dissipation can be done itself in the liquid. Then also almost 100% of the energy going into the process is utilized with the little energy wasted as the ejected heat. So we can the main purpose of providing intercooler is to dissipate the heat, right? So we no need a separate intercooler if you use the liquid piston compression. Then we have another type, rotary compressor. That will come under your reciprocating compressors. So these compressors uses rotors in place of pistons. So in that we have pistons, here we have rotors. So giving a pulsating free discharging air. So these rotors are power driven. So they have the following advantages over reciprocating compressors also. So that are they require a lower starting torque. So in torque wise, the rotary compressors need less torque alone. Then they give a continuous pulsation free discharge air. Then this will give generally provide higher output. Then they require the smaller foundations, vibrate less, and have pressure parts, which means less failure state. Right. So these are the advantages of the rotary compressors. Just the thing is they have to replace the piston with the rotor to get the compressed air. Then the subtypes of the rotary compressors are we have depending on the action of geometry of the rotors. So we classify the rotary compressors as low compressors, screw compressors, then man compressors, then scroll compressors. Right, so in the syllabus we have man compressors. So we will look at what is one by one in the subsequent slides. This is for low compressor, comes under rotary compressors. So also called as a roots blower. It's essentially a low pressure blower and it's limited to a discharge pressure of 1 bar in a single stage and 2.2 bar in a two-stage design. Actually, this is also called as a root blower. So it's like a blower. You know what is blower? And at maximum pressure of 2.2 bar. Right, in the case of two-stage. Then this is your rotary screw compression. Then the rotary screw compressors used to measure rotating positive displacement helical screws to force the air into a smaller space. If you've seen the figure, we are using a two screws. In between the gap of the screws, we can compress the air. Right. So these are usually used for the continuous operations in commercial and industrial applications, and maybe either stationary or portable. So we can use this compressor for commercial or industrial applications. be in stationary or portable. So because of simple designs and a few varying parts, rotary screws, air compressors are easy to install, operate and maintain. So these is the advantage of rotary screw compression. And the rotary screw compressors are commonly produced in oil-fluid and air-free types. Oil-free types. So we have two types of rotary screw compression. So one is oil-fluid, and another is oil-free types. Oil-fluid compressors are nothing but oil-fluid compressors. So oil is used as a medium to cool the compression, where oil seals the internal clearance of the compressor. So you know what is clearance? So the gap between the two rolls. So that can be sealed with these oils. So that will cool the compressor. Through filters are needed to separate oil from the discharge air. So in between the actually the oil and the compressed air is a mixture, the byproduct of these compression. So we have to separate air separately. So cooling takes place right inside the compression, and thus the working parts never experience extreme operating temperatures. So because we are using oil, that will give you a long life, but the disadvantages is we have to separate air from the oil and air. Then the oil-free screw air compressors specially designed air ends to compress air, giving true oil-free air. So to replace that disadvantage, we have this oil-free screw air compression. They are water-cooled or air-cooled and provide the same flexibility as oil-fluid rotary compressors. The thing is, in oil-fluid compression, we use the oil as a lubricant or as a cooler, where in the case of oil-free, we don't have that. Instead, we use the air-cooled and water-cooled. Then this is your rotary band compression. This is one of the type of compression. Then one of the oldest compression technologies is this band compression. Then rotary band compressors consist of a rotor with a number of blades. So you can see this. So these are the rotor. So these are rotor, the number of blades. Inserted in a radial slot and the rotor. So if you rotate these blades, we can get the section and we can compress. So the rotor is mounted outside in a larger housing. Just wait a minute. Right, so this rotor is mounted offset in larger housing that is either circular or more complex shape. So as the rotor turns, it slides in and out of these slots, keeping contact with the outer walls of the housing. So there's a series of decreasing volumes is increased by the rotating blades. So the thing is, we have the offset. So with the use of this offset, if you rotate, there will be a volume increasing and decreasing. So because of that, it can get the compressed air. Then they can be either stationary or portable. It can be single or multi-stage, and can be driven by electric motors or internal combustion engines. We have other types also in van compressors. So they are well suited to electric motor driven drive and is significantly quieter in operations than the equivalent piston compressors. Then they can have mechanical efficiencies of about 90%. So that is the point we have noted. So van compressors can give the mechanical efficiencies about 90%. Then another type of rotary compression is scroll compression. Yeah, spool compressors, also known as spool pump and spool vacuum pump, uses two interleaved spiral-like vanes. So this is your vanes. So we have two vanes. One is fixed and another one is can be moved. So it will be like a spiral-like shape. Then often one of the spool is fixed while the other orbits eccentrically without rotating. So thereby trapping and then pumping of the compression pockets of fluids or gas between the spools can happen. Right? So because of that, so eccentrically it will rotate, it will orbit. So you can get the compressed air continuously also. Then due to minimum clearance volume between the fixed spool and the orbiting spool, these compressors have a very high volumetric efficiency. This will give you actual volumetric efficiency more. Then they operate more smoothly, quietly, and reliably than other types of compressors in the lower volume range. Again, we have the disadvantage. Lower volume range only can be used this compressor. Right. So then we can look what is another type of compressor. That is a dynamic compressor. So the another type other than the reciprocating compressor is dynamic compressor. So in these compressors, velocity of air is increased. So you know very well this is actually the Bernoulli's equations. So in these compressors, the velocity of air is increased, which is converted to high pressure at the outlet of the compressor by varying the area of flow. Right. So in this compressor, a small change in compression ratio produces a marked change in compression output and efficiency. Right. So a small change in compression ratio, produces the output, also the efficiency. So they are better suited for applications involving very high applications, very high capacities like greater than 4,000 CFM. Then the dynamic compressors are classified subtypes of centrifugal compressors and axial compressors. So in this dynamic compressor, the two classification. That one is centrifugal, another is axial. So this is your centrifugal air compression. This will look like just a pump, water pump. So instead of water, we will use the air gets compressed. So this centrifugal compressor uses a rotating disc or impeller. So you can from the term impeller. So impeller is the main part of this centrifugal compression. So in a shaped hosing, push the gas to the rim of the impeller. Right. So this will increase the velocity of the gas. A diffusion that is your divergent duct. So this is your divergent duct. These divergent duct sections also called plenum. This will convert the elastic energy to a pressure energy. So when increased velocity will give you the increased pressure. Both are indirect proportion. Hence we get air at high pressure. So they are primarily used for continuous stationary services in industries such as oil refineries, chemicals and petrochemical plants, and natural gas processing plants. So we can see these kinds of rotary centrifugal compressors in all these applications. They are generally single stage machines, but with multiple staging, they can achieve high output pressures up to greater than 16 megapascal. Then this centrifugal air compressors is an oil-free compression by design. Then the oil lubricator running gear is separated from the air by shaft shields and atmospheric vents. So we can say this centrifugal air compressor is oil-free, but actually we we apply the lubricant oil to cool, but there was separator. So, and this is a continuous output machine. Right, so this centrifugal air compression is a continuous output machine, like your water pump. Then we have another type, axial compression. So this is the diagram of axial compression. So if axial flow compressors are dynamic rotating compressors that use arrays of fan-like airfoils. Arrays of fan-like airfoils that progressively accelerate air. So these airfoils will accelerate air, but we have arrays, right? So the arrays of airfoils are set in a rows, usually as pairs. So if one rotating and one stationary. So if this airfoil is rotating, this will be stationary, and this will be rotating, then this will be stationary. And so we have the range of airfoils. The rotating airfoils, also known as blades or rotors, accelerate the fluid. That here the fluid is air. Then the stationary airfoils, also known as stators. So we have rotors and stators, or we have blades or bands. These bands will decelerate and redirect the flow directions of the fluid. So this preparing it for the rotor blades of the next stage. So we are in advance to prepare the rotorless blades of axial compressors. In our applications, we have this axial compressors with the stators and rotors. So this rotor will increase the will increase the velocity. Then this stators will decelerate and redirect the flow direction. Right, so these axial compressors are almost always multi-stage, where the cross-sectional area of the gas passage minimizing along the compressors to maintain an optimum axial Mach numbers. So this Mach number is actually the ratio between the actual velocity with the velocity of sound. Right, so no need to worry about that. So axial compressors are almost always multi-stage, right? So they are used to where there is a requirement for a high compression ratio, and if you require a high flow rate, a compact design, you can go with this axial compression. Then, so we have these types of compressors. Then how to select an appropriate compressors in this? So that is based on the this NBEE, that is the National Bureau of Energy Efficiency. So we have some standard. So when choosing a compressor, the parameters of suitability are generally the range of the capacity of free air delivery and the working pressure to be considered. Then the general selection of the criterion for compressors is given by the NBEE as follows: that the types of compressors we have, then the capacity range and working pressure to be considered. So if you want the capacity range around 100 to 30,000 metric cube per hour, you can go with the multi-stage, single stage. So you can choose depending upon whatever you want. Right, so this is your National Bureau of Energy Efficiency organization standard. So we can select the compressors in these types, in these all of the types, whatever we want. Then, so this graph will show you how to working range of various compressors. So this is the capacity, compressor capacity versus pressure. So this graph will show you the working range of various compressors. Right, so this range. This range is can be chosen for rotary. If you want this range, this range can be choose for reciprocating, or if you want this range, we can go with the centrifugal compressions. So we can use all the three in this range, or we can use all these rotary and centrifugal in this range. That's these are the working range of these compressors. So we can select based on our requirements. We can select the application of compressors, types of compressors. Right. So we have to look at the components of the compressed air. That is compression. So we have intake air filters, then we have a compressor, then we have interstage and cooler, then we have air dryers, we have moisture drain traps, then we have receivers, then we have distributions through piping. There is a piece missing. So we need piping, right? So we need to distribute the compressed air through piping. So we need this. So these are the parts of compressor, compressed air system. These are the components of compressed air system. So we'll look. The following are the components of a compressed air system, which are crucial to the working of the system. You know, the compressor takes in air and compress it to the required culture. Then good control and maintenance is the key to saving energy. We have the compressor component. So this is the actual body of the compressor, compressed air system. So this will only gets compressed air. So this is your actual vessel. The air receiver is a pressure vessel that acts as a reservoir to store and cool the compressed air. It helps to ensure reduced. Is there any disturbances? Can we continue? Students, are you there? Are you listening?
Yes, sir.
Right. So the air receiver is a pressure vessel that acts as a reservoir. So these are the applications. So it serves as a reservoir for sudden or unusually heavy demands in excess of compressor capacity. So it should prevent too frequent loading and unloading of the compressor. So it should separate the moisture and oil vapors, allowing the moisture carried over from the other coolers. Then another component is interstage coolers. So this will cool the air before it enters the next stage inside the compressor to reduce the work of the compression and increase efficiency. You know what is the purpose of cooler, right? So actually this is the cross-sectional view of this intercooler. So this portion. Right. So this is your cooler. So we can flow the water or whatever medium you want through these pipes. So you can see this cooling water outlet. So we can pass this cooling water inlet through this pipe. Then we can flow the water through this pipe. Then finally we can get the cooling water outlet. So the heat will be transferred to this water. Then we have this compressed air inlet. Then this is your piston cylinders and whatever we have. Then this compressed air will have increased temperature. So this will subjected to contact with this water. Then the temperature will be transferred to the water. Then we have this air outlet. Also we have pressure relief valve in this. So if you want to release the pressure, we can activate this. Also we have separator. So actually this is the cross section view of the water cooled intercooler. We can pass the water through the pipes. Then we can transfer the heat in the compressed air to the water. Then we have after coolers remove moistures in the air by reducing temperatures in water cooled heat exchanger. So we have two types of intercooler. That is, one is air cooler, and another one is we have water cooler. So this is the actual water cooler. So we can pass the water to this. Then also we can employ the air cooler to transfer the heat of the compressed air to the air, to the atmospheric air. Then we have another compound of intake air filters and air dryers. These are the other two components in the compressed air system. So these intake air filters, these both will treat the air to remove the impurities such as water, dirt and oil that are present in the ambient air being drawn into the compression, and those added by the compression. So actually we are using the atmospheric air as a medium of compression. Then this air will definitely will have the dirt and oil in that. So we have to filter that. So because of that, we have this air intake filters and air dryer. Actually, this dirt can be the filter caters to dust impurities, while the dryers remove moisture impurities. So this air filters is to remove the dirt. Then these air dryers is for to remove the oil or all other impurities. So various types of dryers are used, like absorbent dryers. Then we have refrigerant dryers, and we have heat compression dryers. So just make a note of it. So we have different type of dryers that can be employed in the compressed air system. Then the impurities are filtered out with the liquids removed from the system by condensate traps. So these traps resembles steam traps and can be manually operated or timed or automated. So actually the releasing valves, right? So we have a manual drain choke, automatic drain valves. So this is for the filter of the impurities with the liquids, right? So we have this pressure relief valves to remove these impurities with the liquids. Then the systems normally consist of the above components, including distribution systems running throughout the factory to the end use equipment. So we need some piping connections also to supply the compressed air to all the departments of the company. So through the factory to the end user equipment, such pneumatic drills supply through a flexible hose. So we need a flexible hoses to supply the compressed air. Then in the next slide we have a figure that will show you how these components can be set up in the system. Then the arrangement can be more compact in the case of small scale production, and in the case of large scale production, so we need a more complicated arrangement. So actually this is a typical compressed air system with components and networks. So we have this compressor here. We have the compressor here. We can with the air receiver here. So this air receiver is get compressed, and we have stored in a air receiver again a main. Then we have dryers. We have oil separators, oil water separators. Then we have primary filters are there. So Then this is supplied to the main trunk line. Then from this main trunk line, we can connect the branch lines. So this is for actual company setup of a compressed air system. Right. So this is the introduction about the compressor. So we can go the quick through about the air compressor. So the air compressor device which takes a definite quantity of a fluid, usually gas, and most of on air, and deliver it at an required pressure. Right. So this is the exact definition of about the compressor. Then the air compressors take its atmospheric air, then it will compress it, then delivers to the storage vessel, that is the wire. Then compression requires work to be done on this gas. So come to our point. So in this compressor, the work to be done on the gas, right? So W is positive or negative. Work is to be done on the system, so we need negative work. Right? So we need to do work on the system, right? So the compressors must be driven by some sort of drive motors like engines, or so we need minus work. So these are the quick of our classification of air compressors. We have reciprocating artery. That reciprocating, we have number of stages of compressions. We have single stage and multi-stage. So we have based on the slides of pistons in operation, we have single acting and multi-acting. So we have also three type that can be also centrifugal rotary, also a type of air compression. So we in detailed view that classifications. So we have this reciprocating compressors, right? So we can study the work done on the reciprocating compressors in the subsequent slides. So this reciprocating compressors, you know very well, the working of this reciprocating compressor is the single acting piston action in the cylinder or a reciprocating compressor, you know very well. So the piston is driven by the crankshaft via a connecting rod. So this is your crankshaft. So this is your crankshaft. This is your connecting rod. Then this is your piston. Then this is your cylinder. On the top of the cylinder are a suction valve and a discharge valve will be there. So we have a suction valve. So this air inlet will be done by the suction valve. Then this outlet valve will get the compressed, will release the compressed air. That can be called as a discharge valve. Then reciprocating compressors usually has a 2, 3, or 4 or up to 6 cylinders in it. So we can have the number of cylinders in it. So in this we have one cylinder. Also this is a 2 cylinder. So also we can have the series of cylinders connected together. That can be seen in like automobiles. So we have a series of cylinders connected together, multi-stage cylinders, multi-stage compression. Then so we have in reciprocating compression we have these two stroke. One is suction stroke, another one is compression stroke. You know what is suction? Suction is the process of getting air into the piston. Then compression stroke is compressing this air, the intake air inside the piston. So we can call this two stroke. That is, one is suction stroke and another is compression stroke. So this is your PV diagram of this reciprocating compressor. So actually, so we have this suction and compression stroke, right? So this is 1 to 2. Wait a minute. class like right, sorry for the disturbance. So we can continue. So this is the PV diagram of our compressor, reciprocating compressor. We know very well. So we have the processes 1 to 2, 2 to 3, 3 to 4. So in process 4 to 1, we will get the suction. Then we will compress the air in the process 1 to 2. Then again there is expansion. Then again there is the suction. There is compression. Then expansion. So you know the process of reciprocating piston cylinder arrangement. So the process 4 to 1 will be the volume V1 of air aspirated into the compressor at P1 and T1. So this 4 to 1 process. So we will suck the air. Then in process 1 to 2, the air compressed according to the equation of polytropic process, that is PV power n is equal to constant. So from P1 to P2, so we will get the compressed air. So the pressure of this air gets increased, right? So from P1 is low pressure and P2 is high pressure. We can get the high pressure air by the use of this 1 to 2 process, the second process. Then also the temperature increases from T1 to T2. So you can see this. So you know this is not the same isotherm. So this is another isotherm. Then the state 2 is another isotherm. So the temperature definitely will increase. Then in the process 4 to 3, the compressed air at the P2 and V2 with the temperature T2 is delivered. Right, so we can get the compressed air in the process 2 to 3. So this is an actual reciprocating compression. So we can have the compression with all these three available processes. So we can have the isothermal process. So we can have the adiabatic process. So we can have the polytropic process. But here we are using the air as a medium for reciprocating compression. So during compression, due to the excess temperatures above surrounding, the air will exchange the heat to the surrounding. Right. So the compression index n is always less than mu, less than gamma. Then the adiabatic index. Right. So we can go with the adiabatic process, that is PV power gamma is equal to constant. So as the compressor is a working wood consuming device, every effort is designed to reduce the work. So in the process 1 to 2 double dash, the adiabatic compressions showing this. This dash line 1 to 2 double dash, we have the polytropic expansions. So adiabatic compression that can be give the maximum work. Then in process 1 to 2, polytropic compression. Then in process 1 to 2 dash, that is isothermal compression, that will give you the minimum work. This is our isothermal, the red lines will give you the isothermal. So we can compare the work done on the system, right? So we can calculate the area under the curve is done. So we can assume this. So this is the area under the curve is less than the area under this adiabatic curve. So we can compare. So the maximum work to be done on the adiabatic compression, and the minimum work is enough to work is enough in the isothermal compression. So this comparison between the isothermal work and actual work is important in this reciprocating compression. So we have the isothermal efficiency equation as you know, isothermal efficiency is equal to isothermal work by actual work. So thus more the isothermal efficiency will have the more actual compression approaches to the isothermal compression. So we have actual work as the area of 41234. So the 4 1, then we have 2 3 4. That is our actual polytropic process. That is our adiabatic process. So that is our actual work. So that can be calculated with the difference between the area of 4 1 minus area of 1 2 minus area of 2 3. So I can calculate the area of 4 1, area under the curve A 4 1, and minus 1 2 and minus 2 3. So if you calculate this, we can have the area. This actually the first process. So area 4 to 1 is your constant pressure process, right? So we can have the equation as P1 V1. Then we have minus this area under 1 to 2. We have the P1 P2 V2 minus P1 V1 by n minus 1, and the area of the process 2 to 3 is P2, again constant pressure, right? So we can have the P2. So from this we can take the P1 V1 minus P2 V2 outside, and we can write the equation as like this. Then we can change. We can multiply the minus symbol and this to get the plus symbol. So this minus symbol is taken out, get plus, right? So this symbol is changed to plus. Then we can have the this minus P1 V1 into P1 V1. Then this plus P2 V2 into minus P1 P2 V2. Okay, so because of that, we can write the equation like this. So we have the equation as V1 V1 minus P2 V2 plus P1 V1 minus P2 V2 by n minus 1, right? So here we have P1 V1 minus P2 V2, and also here we have P1 V1 minus P2 V2. We can take the terms outside. Then finally we can have the equation as P1 V1 minus P2 V2 into 1 plus 1 by n minus 1. Then also we can reduce this equation. Then this n minus 1 plus 1 divided by n minus 1. So plus 1 minus 1 we cancel. Then we can have the n by n minus 1. Finally, then we can take P1 V1 outside in this equation. Then we can have this 1 minus P2 V2 by P1 V1. Then we know for polytropic process we have a P1 V1 power n is equal to P2 V2 power n. So we can replace P2 by V1 equal to P1 by P2 power 1 by n. So finally we can have the isothermal work as n by n minus 1 into P1 V1 minus here instead of V2 by V1. We can replace P1 by P2 power 1 by n. Then for isothermal work done, so we can have the same equation. So this is the same equation what we seen in the previous. Then what we can do, there is 1 by n, P1 V1 here. So we have P1 P2 by P1 here, and we have P1 by P2 here. So we can reciprocate this. We can write the reciprocal. Then we can write the P2 by P1 power minus 1 by n. So here is 1 by n. So if you want reciprocal, so we can write minus 1 by n. So here we can write the whole term. So we have P2 by P1 power 1 into P2 by P1 power minus 1 by n. Then that can be written as n minus 1 by n. Then finally we can write the isothermal work as n by n minus 1 into this P1 V1 can be written as m RT1. Then 1 minus P2 by P1 power n minus 1 by n. So this is the final isothermal work equation. So the solution of this equation is always negative, you know very well. Why? Because we are doing work on the system. So this this shows the work is done on the compressor. So this is an actual work done on the isothermal compressor. Then we have the clearance volume, right? So if you look at the piston cycle arrangement, there will be clearance provided. So that clearance volume also to be considered in the equation of work. So we can see that. So this 1 to 2, port 1 is our actual strut volume, effective strut volume. Then this volume, right? So we have this V3, this volume. So that is our clearance volume. So actual strut volume can be calculated with the equation V1 minus V3, that is the strut volume. Then the effective strut volume can be calculated with the V1 minus V4. Then the total volume of the cylinder, piston cylinder arrangement will be your V1. Then, so what is clearance volume is the volume that remains inside the cylinder after the piston reaches the end TTC. Right, so end of its inward stroke. So thus the effective stroke volume can be V1 minus V4. The actual work can be again calculated with this clearance volume that your so area of 1, 2, 3, 4. So this is your actual work. So that can be calculated. So area of 5, 1, 2, 6. We can calculate 5, 1, 2, 6 minus 5, 4, 3, 6. 5, 4, 3, 6. So if you want to consider this clearance volume, we have to neglect this area. So we can again work out the equation for work by reciprocating compressor the same manner. So the also we have the volumetric efficiency, the ratio of free air delivered to the displacement of the compressor, that is our effective strut volume, to the strut volume, that is presence of clearance volume will give you the volumetric efficiency less than 1. So we have the volumetric efficiency equation as effective strut volume divided by strut volume. That you know the equation, that is V1 minus V4 divided by V1 minus V3. So we can have the clearance volume as a clearance volume by strut volume. The clearance ratio as clearance volume by strut volume, that is your VC by VS. That can be your gamma, that is around 4 to 10%. That is the clearance ratio. Then the increased pressure ratio will give you the increased effect of the clearance volume. So the clearance air expansion through greater volume before intake. The cylinder bore and the stroke is fixed. So that will give you the effective strut volume decreases with the increased pressure ratio. Then we can get the decreased volumetric efficiency. So the volumetric efficiency can be calculated with the V1 minus V4 divided by sorry, so we have more to see. So we can go faster. So again we have derived the equation of our work. So this volumetric efficiency can be calculated with the this strut volume, effective strut volume will be strut volume. Right. So we have also we can take this. So we have in the denominator we have V1 minus V3. So we can take that outside. So we can implement this plus V3 and minus V3 in is V1 minus V4. So this is plus V3 and here minus V3 is added with this numerator. Then finally we can get the equation as V1 minus V3 plus V3 minus V4 divided by V1 minus V3. Then we have this V1 minus V3 and both the term we can take that as common. So we can have the equation as 1 plus V3 minus V4 this one divided by V1 minus V3. Then we can take this separately and we can write that is 1 plus V3 by V1 minus V3 minus V4 by V1 minus V3, and we can multiply and divide by V3 in the numerator and denominator. Then we can have 1 plus V3 by that same thing, right? So we can so this V3 by V4 by V3 can be taken outside. Then we have this V3 by V1 by V3. And the same equation. So this also can be written as 1 plus V3 by V1 minus V3. So this V3 by V1 minus V3 can be taken outside. Then we can write this as 1 minus V4 by V3, right? So we can take this outside. So we can have the equation as 1 plus V3 by V1 minus V3 into 1 minus V3 by V4. Then this also can be rewritten as V3 by so minus is taken outside. This minus is taken outside and multiplied with this. We can have 1 minus V3 by V1 minus V3 into V3 by V4 minus 1. Then we know V3 by V4 equal to V3 by V4 power 1 minus 1 by n. That can be replaced here. Then we can have the final equation as that this is your clearance ratio. So the volumetric efficiency can be 1 minus gamma into your V3 by V4 power 1 by n minus n minus 1. So this is your theoretical QB diagram. So right, so just remember this formula. So if you want the volumetric efficiency of reciprocating compressor, just remember this formula. And if you want the work done, equation of work for the reciprocating compressor, just remember this. Remember this equation. Right, so remember this equation, that's enough. If you want to derive this equation, just you have to open it. Right. So where we are? Yes. So this is your theoretical QB diagram. So in real, we have these jumps because wall bounce and receiver pressure. So what is wall bounce and what is receiver pressure? So at point 4, so this is point 4. So just your intake will happen, right? So inlet walls does not open due to. So in this point 4, we have to the inlet wall is open, but it does not open due to there must be a pressure difference across the wall to open, and also there is a inlet value inertia. That is inlet wall inertia. So because of that, we have this wall bumps. So pressure drops continues till sufficient level for wall to force its seats. So some wall bounce is set, that is the wavy line. So eventually the pressure sets down at a level lower than atmospheric. So this negative pressure difference is known as intake depression. So because of this intake depression, we have this wall bounce. So similar situations appears at point 2 also. Actually, this the exit valve will open, right? So at the start of this delivery, so the pressure rises followed by the valve bounce, and then the pressure settles at the level higher than the delivery pressure level. So the air delivery to the tank or receiver ends generally known as receiver pressure. So we have the intake pressure, the inlet level, and we have a receiver pressure, and the point 2 on the at the air delivery level. So because of that, we have these kinds of actual PV diagram. So we need to calculate the free air delivery. So what is free air delivery means? If the volume of the air compressor is reduced to atmospheric temperature and pressure, this volume of air is called the free air delivery. Right. So the pressure and the temperature is at atmospheric level, so we can call this as free air delivery. So we can have the equation as T, it is our atmospheric temperature, atmospheric pressure, and atmospheric volume. So that can be written as our that for process 1 to 4, we can have P1 into V1 minus V4 divided by T1, and in the process 2 to 3, we can have P2, that is the change in velocity, change in volume, right? So we can have V2 minus P3 by T2. So if the clearance volume is neglected, so this is because of the clearance volume. So if the clearance volume is neglected, we can have the equation as in general PV by T is equal to T1 V1 by T, T1 equal to P2 V2 by T2. Then if you substitute these atmospheric values, so that can be your free air delivery. Right. So if P1 is 1.3 to 5 km per meter square, that is for atmospheric pressure. Also, the temperature will be around 288 Kelvin. So that can be the system. The compressor can be your free air delivery. So this question will be asked in 2 marks. Then we have a reciprocating compressor, multi-stage. So from the regenerative Brayton cycle itself, we are noticing this multi-stage compression. So high pressure occurs by a single stage. So these are the disadvantages of single stage compressors. So this requires heavy working parts. So it has to accommodate the high pressure ratios. Then increases balancing problems. Then high torque fluctuations. Then requires heavy flywheel relations. So these are the disadvantages of the single stage. Then this will demand the multi-stage. So for that we have this multi-stage reciprocating compressor. So we know very well there are stages. So we have a low pressure cylinder and the intermediate pressure cylinder, and we have high pressure cylinder. So in between cylinders we have this intercooler. You know what is the purpose of intercooler. So if air gets intake in this low pressure cylinder, then it will compress the air some extent. Then again it will subject it to intercooler. Then again it will take into the intermediate pressure cylinder. Then again it gets compressed. Then again it will pass through the intercooler. Then again it will send to the high pressure cylinder. Then we can get the high pressure delivery as an output of this high pressure cylinder. Then this series of arrangement of cylinders in which the compressed air from the earlier cylinder becomes the intake of the next cylinders. You know very well that LP states low pressure and IP intermediate pressure, HP high pressure. Yeah. Then you know what is intercooler. So this compressed air is cooled between the cylinders. Then this is your reciprocating compression multi-stage PV diagram. So this is the low pressure cylinder. This is the high pressure cylinder. So So this intercooling is happening in this region. So low pressure and intercooling, and again compression, then again intercooling. So this is your without intercooling PV diagram. Then this is for perfect intercooling PV diagram. We discussed in the earlier slides also very well. Then we have the overall pressure range from P1 to P3, and we have a single stage cycle. So this is 8156 is our single stage cycle. So 8156 is our single stage cycle. So without intercooling, we have low pressure, that is 8147 will give you the low pressure, and this 7456 will give you the high pressure. Then with intercooling, this 8147 again is low pressure, and 7236 is your you can differentiate it. 7456 is your high pressure, and in the case of with intercooling, we have high pressure as 7236. Just you can go through the PV diagram, then you can compare that. Then this perfect intercooling is after initial compression in low pressure cylinder, air is cooled in the intercooler to its original temperature before entering high pressure cylinder. So that is because we have to increase the temperature, that is T2 equal to T1, or the points 1 and 2 are the same isothermal line. So why? Because we explained it in detail. So we should keep the T1 and T2 in the same isothermal. So in a single stage compression, so the stages where the Douglas, then the delivery temperature that can be T5 by T1 is equal to T3 by T1 power n minus 1 by n. Where in the case of two-stage compressors without intercooling, we can have this equation. So we have two stage. So because we have addition of the stages, the work. Then this is without intercooling. So this is same as the work done in a single stage. Delivery temperature also remains same. So if there is a two stage, but there is no intercooling, means the process is like a single stage compression. But we have with the perfect intercooling means we can get the improved. Just we can compare the formulas. So if you compare the formulas, we can get the improved outcome. That will reduce the outcome. Also, we have the delivery temperatures. That is T3 by T2 is equal to T3 by the same equation. Just we have to write accordingly what states are there. And also we have a T2 is equal to T1 for perfect intercooling. So this equations are same. So we know this with perfect intercooling we have T2 is equal to T1. So we can have P2 is equal to P1 V1. Also we have P4 is equal to P2. So we can compare this P4. Pressure 4 is equal to P2. Yes, pressure is same, right? So we can write the final equation of W as like this. So we can have n by n minus 1, T1 V1 into 2 minus T2 V2, T2 by V1 power n minus 1 by n minus P3 P2 by n minus 1 by n. So this shaded area. So this will give you this shaded area. This area. So this work saving due to intercooler. So because of the intercooler, we are saving the work. So this is our actual mission of this intercooler. Then the condition for minimum work can be derived from the PV diagram. So for intermediate pressure, P2 will give you the P1 from the will be 0, right? So then the in this process 24532 also the outcome will be 0. So there is an optimum P2 for which the area of the curve 24532 is maximum. So we can get the maximum work is minimum with this perfect intercooler with the multi-stage compressor. Then finally we can have this equation for minimum work as W is equal to N by N minus 1. Same equation, right? So for minimum work we have to differentiate this with the P2 for second stage pressure. So if you differentiate this with the P2, just use the differential equation. Just you have to differentiate this equation with the P2. So we can, if you differentiate, finally we can have this equation. Just use the differential equations. Just go with the max. Then we can have this final equation. Then we can neglect the terms whatever we want. So finally we can have this P2 over 1 minus n where it was here. We can have this n minus 1 by n minus 1. So finally we can have this P2 power. So we can neglect these two. So this will be same, right? Right. So this will be same. So we will omit that. We will cancel that. Then finally we can have this P2 power minus 1 by n divided by P2 P2 power minus 2 plus 2n plus 1 by n equal to P1. Yes. So here we are having 0, right? Equal to 0. So we are taking this to the right hand side. So finally we will have the equation as P2 square will be equal to P1 P3. The thing is the P1 by P2 by P1 will be equal to P3 by P2. Right. Or we can write the P2 is equal to square root of P1 P3. So that is the thing. So P2 obtained with their conditions, that is the pressure ratio for stage is equal. So it's the ideal intermediate pressure with perfect intercooling give the minimum work. So we have the equal work per cycle as the final equation. That is work 2 n by n minus 1 by P1 V1, the same equation. Just you can go through that. So this is your actual minimum work if you provide the multi-stage intercooling. Then we need to find the efficiency, thermal efficiency of the reciprocating compressor with the perfect intercooling means we can have the isothermal work done by cycle will be P1 V1 natural logarithm of P2 by P1. That's you know the formula. Then isothermal power can be calculated with this division of 60 into 1000 kilowatts. Okay, we are changing the power. I think we have 2-3 slides, so just we can complete the conversion unit 2. Right. So the indicated power can be calculated. So the power obtained from the actual indicator card taken during the test on the compression. Then compression efficiency can be calculated by the use of a formula isothermal power by indicated power. Then the isothermal efficiency will be isothermal power by shaft power. So these are the general equations. Just you can refer that. Then the adiabatic efficiency can be calculated with the same formula W by brake power required to drive the compression. So this mechanical efficiency can be calculated with the formula integrated power by shaft power. So these are the general equations for the efficiencies of reciprocating compressors. Just you can go through that. Then how to increase the isothermal efficiency? So if you want to increase the isothermal efficiency, we need to speed injection. So accumulations of water into the compressor cylinder toward the compression stove. So the object is to cool the air for the next operations, right? So we have to be careful while spraying the injection. So the demerits of this spraying injection requires a special gear for injection, and it should need injected water interfaces with the cylinder lubrication. So it damages to the cylinder's walls and valves, and it will water must be separated before delivery of the gas system. We can improve the thermal efficiency, isothermal efficiency by spray injection, but we have these demerits, so we have to be careful. Then also we can improve the isothermal efficiency by water jacketing. So that circulating water around the cylinder to help the cooling of the air during compression. So we can improve the efficiency. Also, we can improve the efficiency by intercooling. So for high speed and high pressure ratio compressors, the compressed air from the earlier stages is cooled to its original temperature before passing it to the next stage by the use of an intercooler. Then the external fins also to be provided for the improvement of efficiency. Also, we can give the cylinder proportions to get the improved efficiency. Then, so we can also give the clearance volume. So it consists of two spaces. So space between the cylinder and the pistons to allow the wear, and space for the reciprocations of valves. So we know why we provide the clearance volume. So high class, high pressure compressors have the clearance volume around 3%. Then low pressure compressor have the clearance volume around 6% of set volume. This we can compare. So the effective clearance volume should be volume taken in per stroke should be less than stroke volume. So that will give you the increased size of the compressor, and also will give you the increased power to drive the compressor. So we have to be careful while choosing the clearance volume. Then again, this is where reciprocating compressors work done. So again, the same equation for W. So this is your actual compression expansions for the same law. So in this case, we have the P3 is equal to P2 and P4 is equal to P1. Then we can replace the equations, and we can finally get the equation as W is equal to N by N minus 1 into same equation, right? So Coulomb per kg of air delivered can be calculated. So we can neglect this mass. So that can be your W, capital W, that is N by N minus 1 into RT 1 into 1 minus P2 by P1 power N minus 1 by N. Don't fear. So this is the same equation. So that was written here. So that's it. So compressors. So we have different types of compressors. So compressors are widely used in the industries. So we have to choose the compressors depending upon our requirements. So that's it. So we can start the third unit in the next class. So if time permits, can you arrange the tomorrow afternoon for our thermodynamic class? Right, that can be discussed with the class rep. So we can finish it off. So if you have any queries, you can ask now, or else you can hang up. Thank you. Have a good day. The announcement will be made through your presentation for the tomorrow class. Do you have any queries? Students, are you there?
Sir?
Do you have any queries, Ma?
No, sir.
In these compressors. Okay. Okay. Thank you. Thank you.
Thank you, sir.
Okay. Jaraman.
சார்
நாளைக்கு மதியம் நம்ம ஃப்ரீயாமா? நாளைக்கு மதியம்
நாளைக்கு
வர
மதியம்
நம்ம சாட்டர்டே அவர் மிஸ் ஆயிடுச்சு இல்லையா? அதுக்கு பேசலாம்.
மதியம் எத்தனை மணிக்கு சார் எடுக்கிறீங்க?
மதியம் உங்களுக்கு ஃப்ரீ தானே? மதியம் உங்களுக்கு கவர்ல இல்ல?
இல்ல சார்.
அது எடுத்துக்கலாமா?
சார் ஃப்ளூட் மெக்கானிக் சார் எடுத்துக்கிறேன்னு சொல்றாரு சார்.
யாருமா?
சேக் சார் எடுத்துக்கிறேன்னு சொல்றாரு சார். அவர்கிட்ட கேட்டு சார்.
இல்ல அதான் எடுக்கணும்னு சொல்லியிருந்தாருன்னா அவர் விட்டுறணும். ஃப்ரைடே மேம் கிளாஸ் இருக்கு, லேப் இருக்கு உங்களுக்கு.
நான் சார்கிட்ட கேட்டு இன்ஃபார்ம் பண்றேன் சார்.
ஓகே. அதான் லேப்ஸான கிளாஸ் தான். அந்த சாட்டர்டே நம்ம மிஸ் பண்ணோம் இல்லையா? அந்த கிளாஸ் வந்து ஒரு 2 ஹவர் எடுத்துடலாம். எப்போ டிஸ்கஸ் பண்ணிட்டு சொல்லுங்க. சரியா?
ஓகே சார். ஓகே சார்.
ஓகே. தேங்க்யூ.